Okay, let's get started. I have a lot of ground to cover. There's only a few lectures left. So I think just to give you guys a warning, I may go a little bit faster today. If there's something that's not clear, slow me down and we can talk about it. But uh, again, just to reemphasize, we've covered the fundamentals. So now we're just looking at some periphery issues, which are very important, but certainly are not as fundamental. Um, so let's jump back in. So last lecture we started looking at substrate coupling. And is there a question? No? Okay. So one of the important points about substrate coupling is to know, first of all, what your substrate material is made of. And just knowing that it's silicon is usually not enough. You need to know a little more than that. And there's two big flavors of substrates that you may encounter. And one is sometimes called the epi substrate, and then the other substrate is called appropriately the non-epi substrate, or sometimes the bulk substrate. But there's a huge difference between them. So one, if you look at the substrate, it's moderately conductive. It's on the order of, let's say, 10 to 20 ohm centimeters, maybe as high as 100, maybe as low as 1 ohm centimeter. So it's a resistive piece of material. The other extreme, which is the epi substrate, is very conductive. And so here you see it's about a milliohm centimeter substrate, or within a factor of 10 of that. And because you can't grow transistors in this conductive substrate, you have to have an epi layer. And this is a layer that's grown on top, and that's what gives rise to the name. Now let's look at how these two substrates are different. Well, probably the first person to look at this issue and to write about it was a group at Stanford, Bruce Woolley and his students. And they took an experimental approach, and they put down some transistors, they put down some test structures, and they looked at this problem. You know, how much of an issue is this going to be if you're going to build high-density digital circuits and analog circuits near each other? And so in their example, they have, maybe we can zoom in here to see this more clearly. So you've got this ring oscillator that's on chip that's driving a capacitive node. This capacitor couples to the substrate through its backplate parasitic and also through the drains of these devices, right? The NMOS and PMOS devices here are also capacitively coupled to the substrate. In this case, the NMOS is more so because they don't have a well around them. And then some distance away, they lay out a transistor and basically bias it up and observe the voltage waveform coming out of the drain of that device. Now you'll notice that this is an epi substrate. It has a very conductive substrate. And one of the things that they don't do in this paper is they don't put a contact on the backside of the substrate. In other words, they don't ground the backside of the substrate. And as we'll see, that has a severe impact on how much coupling you get. You can, in fact, get a lot more coupling. So this is the experimental setup. These are some of the waveforms they observed. You can see here that as you have a switching event sometime later, you have a voltage waveform, you know, basically that this might be the rising edge, this might be the falling edge, or vice versa. And these are the voltage spikes that you observe on the drain of that transistor. Now, that transistor, remember, is not connected to anything, so any voltage on the drain is substrate coupling. And you see the magnitude of the voltage is quite large. It's on the order of tens of millivolts. And the settling time for this transient to die out is actually quite significant. Up here, about 7 nanoseconds to get down to just 1 millivolt. So if you want it to get down even lower, you're looking at maybe 10 nanoseconds. So if you're building a system and you're sensitive to noise on the order of a millivolt, right, this is going to be an issue. If you look at the current waveform in the substrate, of course you can't really do that. You can do it indirectly, you can do it thermally, but it's a very small current. So you're going to have a hard time seeing that current. So you have to resort to simulation. So you run some simulations. Basically you mesh up the substrate as a distributed resistive network, and you can then look at the currents in the substrate. And you find that for this epi kind of substrate, current is flowing everywhere. This piece of material here is acting like a very low resistance that's connecting every point on the chip to every other point on the chip. So the current flow you can see is uniform in this direction, and it's going pretty deep in the substrate. How do we model this effect? Well, it turns out the model is exceedingly simple. It's basically two contacts. So this is one transistor, or this is one capacitor. This is another transistor. And the network that couples them is just a simple resistive network. And so this resistance here is the resistance to get through the epi material, let's say. And then this resistive network here is a network that tells you how much coupling you have from this contact to this contact, and also how much ground current you have in case you ground the substrate. Even if you don't ground the bottom of the substrate, this network still needs to be there. Why is that? So let's look at a picture again. So the picture is I've got my substrate, which is a line. I've got a contact here and a contact here. And basically, I know there's some resistance between them, right? And I'm claiming that even if I don't ground the actual substrate, I still need these two resistors here. Why is that? Oh, okay, I cheated a little bit. I didn't show you the whole picture. Well, you know that there's always ground contacts at the surface, right? This is what we call a substrate contact, or a substrate tap, right? So either advertently or inadvertently, we are going to place several contacts like this around our chip, right? Anytime we lay out a transistor, we do this, right? For instance, if I have a NMOS device, I'm going to put a substrate contact right near it in order to make sure that it's grounded. So if this were, let's say, an N plus region, and this is a P substrate, I put a P plus here to make sure that the body of the transistor has a well-defined potential. So this current here going to ground can either be the current going to the surface, or if we actually do contact the backside of the substrate, it's the ground current. Of course, in general, it's both. Okay. Now, why is it that I can get away with modeling my substrate with this simple resistive network? Right? Substrate, after all, is a semiconductor, right? And in device physics, when we study it, we worry about drift, diffusion current, right? At high frequencies, we know that there could be displacement current flowing through the substrate, right? So why is it that this resistive network seems to work well? Anyone want to take a stab at it? Okay, you guys are shy today. Well, it turns out that, in fact, sure, there is displacement current and there's conductive current, and you have to take both into account, right? So conductive current is proportional to sigma. Displacement current is proportional to omega times epsilon, right? And at any given frequency, in a good conductor, this term, the conductive current, totally outweighs the displacement current. Okay, what displacement current is nothing but capacitive current, right? That means I'd have to put capacitors in parallel with these resistors and take into account the fact that current is flowing through this material capacitively. Well, that's in fact how we define a good conductor, is we define a good conductor as having conductive current, which is much larger than displacement current. Well, you can see that only applies up to a certain frequency. And we can in fact define that frequency, and it is done so as the dielectric relaxation frequency. And that's the frequency, if you're below it, it's conductive. If you're above it, it's displacement. And so if I plug in some typical numbers here, let's say for the non-epi substrate, the conductivity was about 10 ohm centimeters. And got to convert that to Siemens per meter to plug into this equation. It works out to 10 ohm centimeter is also 10 Siemens per meter, and then invert it. So anyhow, this works out. Even if it's off by a factor of 10, don't worry about it, because you'll see the numbers come out nicely. I plug in epsilon 11.9 for silicon, and I get about 100 gigahertz. So if you have a substrate with resistance 10 ohms meter, I did make a mistake. This should be this, but still, it's an order of magnitude fine. It turns out that at the end of the day, it really doesn't matter. That the frequency where the displacement current dominates is really high. And so for all practical purposes, the currents flowing in the substrate are just conductive currents. Okay? And we're going to neglect the minority carriers. We're just going to assume the majority carriers are mostly responsible for this current flow, because we're talking about distances much greater than the minority carrier diffusion links. And so then that complicated device physics goes away and you're back to Ohm's law. Okay? Yes?
Question, go back to that. What if the rho is much lower, like the 10 milliohm, whatever stuff like that?
Well, remember
sounds like megahertz, 100
yes.
megahertz.
Then you have to worry about displacement current. But let's look at what we actually have. So I said rho can be on the order of 10 ohms centimeter to, let's say, a milliohm centimeter, right? So this works out to be 10 Siemens per meter, and this would work out to be 10 kilosiemens per meter, right? So for both of these cases, so this is sigma, not rho. So for the case that we've studied, this is the worst case. The non-epi substrate is the worst case. And even that, if you plug in the numbers, you get like 10 gigahertz. Well, you can just, it doesn't really matter, right? I could just move rho down here. But trust me, I've run the numbers, and it works out that for the range of substrates that we care about, it's not an issue. Okay? All right, so this model is really simple, but it's also very intuitive, because it tells me that, let's say that this body is very conductive. If the body is very conductive, draw a picture here. I have these two layers. And let's say I'm worried about this. So I'm looking at the coupling versus distance. So if I move this contact back, how much does the coupling change? In other words, does my crosstalk improve? And so let's say we're talking about an epi substrate. Is it going to help a lot to move back and forth? Okay, Michael, you have an opinion?
I don't think so, because you go down to the low ohmic one and then it's short anyway.
Exactly. What the way to think about it is this is almost a dead short. So really the resistance is dominated by the epi portion. So that there's one resistance to go down, then almost a very small resistance, right? So let's just say 100 ohms, then like 2 ohms, and then another 100 ohms. And if I go way out here, I change like 2 ohms to 4 ohms, but who cares? That's a small fraction of the total. And that's borne out in measurements and more detailed simulations. For a heavily doped substrate down here, you can see that as long as the distance gets to a certain critical threshold, then it really doesn't matter. You know, I can go from 50 microns to 200 microns, and the peak-to-peak noise voltage that I'm picking up is practically the same, right? And on the other hand, with a lightly doped substrate, you see distance matters. So as I increase the distance, I see almost a linear drop in in the noise pickup. And again, with this model, it makes sense, because for a highly doped substrate, this resistance is a major part of the total resistance. So as I increase the distance between these, increasingly the substrate material just looks like a resistor where current is flowing in this direction, and changing this length changes that resistance. The further out I go, the deeper the current can go, and that changes things a little bit, so I go a little bit away from linear. But for the most part, because this is an important fraction of the total resistance connecting these nodes, increasing this does improve the isolation. Okay? All right, so that's actually one of the most important things to know, that if you have an epi substrate, then using distance for isolation really doesn't help you much. You know, there's a critical distance, so obviously you're not going to put a sensitive analog circuit 2 microns away from a noisy digital circuit, but for reasonable distances it doesn't really matter. But in a non-epi substrate, it does help to isolate things with distance. Yes,
Can you
question?
explain why at very low distance that kind of
Yeah, that also makes sense, right? So at very low distances, so I'm getting coupling also through this layer. Even though this layer is so much more conductive, right? Then, so if I have a really far away distance, it doesn't make any sense for current to flow here, right? Because this material is very resistive. So most of the current will flow through the body, the bulk. But for very close distances, it's the epi that's contributing. And so if the epi is contributing, getting far away does help. And so initially there is some help, but then it's all the body that takes over.
So I guess the thickness of the epi really counts for that kind of thing, right?
Exactly. So this distance is on the order of the epi thickness. Yeah. Good question. Okay, so the other thing we might want to do is shield it, right? We learned that last lecture we talked about shielding, and we thought, okay, you know, if you have capacitive coupling between circuits, we can shield it. Similarly, resistive coupling, if I have resistive coupling between circuits, if I put a shield around one circuit and ground it, that would capture all the current and prevent it from intercepting with my circuit. So here there's a noisy digital circuit, and this is a sensitive analog circuit. If I could somehow put this in a box, a cage, and then ground my cage, very importantly, then all the current flowing here would just hit my cage and go to ground. It wouldn't go into my sensitive analog circuit. Unfortunately, I can't build a cage around my device, right? So the best I can do as a circuit designer, you know, I can't change the process, is to put down what's called a guard ring. And this is just a ring of substrate contacts. So if this is a P substrate, this would be a P plus ring that I ground. And what I'm trying to do is intercept the current flowing from here to here and prevent some fraction of it from getting to my circuit. Okay? Let's talk about this. Is this going to work? It's going to be useful. Well, first off, it has a name already, right? And you've probably heard that name. It's probably useful. But which case is it going to be more useful, for the epi substrate or for the non-epi substrate? So how about someone in the back row? Sang, you want to take a stab at it?
Probably for non-epi substrate.
Okay, that's right. And how come?
From the previous slide, that epi slide has no problem if we just get some reasonable distance. So.
Okay, actually this previous slide is essentially the right picture. The idea is that if I look at this for a non-epi substrate, the problem is the current's flowing deep in the body, right? Not much current is flowing here. And if I put this ring now around my device, so this P plus ring, or let's P plus ring, and I ground it, so, and this is the contact that I'm trying to protect, the problem is the current's going under. And so it has no problem going under that ring of protection, so-called protection, and just reaching my circuit, right? So for an epi substrate, the guard ring is not going to work. And in fact, you can see it in measurements and in simulations. Um, Again, this is, I believe, from the same paper, so this is the peak-to-peak noise voltage pickup with and without the guard ring. And of course, it's hard to tell which is which. But let's assume that the one that's smaller is with the guard ring. So okay, things are getting better, but hey, not much better. So I will go from 8 millivolts to 10 millivolts to 8 in this case. But for far, this is for close coupling. If I go to far distance, then actually it makes no difference. Almost the same voltage. And that kind of jives with our understanding of the current for far distances is mostly flowing in the body. And then what's interesting here is there's a difference between these experiments. In this experiment, there's a dedicated package pin used for the guard ring. In other words, this guard ring goes to a separate ground, right? Instead of using the global ground, which is connected to the substrate, I go to my own separate ground contact. And in that case, it does help. But if I just tie this to the substrate contact to the global ground, actually the coupling gets worse. Any explanation for that? Well, it could be one of several things, but you know, remember from last lecture, ground is kind of a dirty place as well. Ground has bond wire inductance, and there's probably more current flowing to ground than current flowing into your dedicated guard ring ground. So the LDIDTs are larger on the ground than they are on your, so let me draw a picture. So again, I have my sensitive node, I put a ring around it, and let's say I tie it to separate ground. Then this is a pretty quiet node. Not much current is flowing through here. So if I have an interference and it's going to ground, you know, it's capturing some fraction, let's say 1 or 2%, maybe 10% of the current that's reaching here. But if I now tie this to the global ground, so chip ground, then there's lots of current going through here. So this is actually rippling, and this is acting like an additional noise mechanism. So it's taking all this noise, placing it close to your circuit, and injecting it in. And so things actually get worse. And so you see, for these cases, regardless of the distance, in both cases you pick up about the same noise. So be careful. If 2 lessons. Lesson 1, epi-substrate guard rings don't help very much. Lesson 2, they help a little bit, but be careful how you ground it, because if you ground it incorrectly, it makes things worse.
Does it help if you don't ground it at all?
No, because then it doesn't do anything, right? It's just floating. Yeah, you have to ground it.
Does it help if you make the ring a little bit larger? Is there an optimal size?
There is an optimal size, and again, the larger you make it, the more noise you pick up, right? And so there is, if you make it too large, it actually starts hurting you. If you make it too small, you're not capturing enough current. So there is definitely an optimal size. Here's a, yeah, I think I'll just skip this and make one more point here. So the backside contact is very important. So we have, especially in an epi-substrate, because current can flow deep, if we can ground the backside, then we can intercept a good fraction of the current, right? So if current is flowing here and there's no ground, it couples very well. But if there's a ground, then some of the current is actually going to flow to ground. And so that should improve our isolation. Unfortunately, it's impossible to put a perfect ground to the backside. There's always going to be some kind of bond wire inductance. And again, we can do an experiment or a simulation, and we can see that the noise pickup is really strongly dependent on that inductance. So for high values of inductance, let's say you're picking up 8 millivolts, as you reduce that inductor down, the coupling almost goes away. So for an epi-substrate, this is by far the best thing you can do to reduce coupling, is have a good packaging technology. Okay, I mean,
Are all these measurements for a spike, the same digital spike?
these are for like digital, yeah, switching waveforms. Yeah. Okay, Here's some papers just to give you some references. No need to zoom in on here, but on your own, if you're interested in this problem, there's some good papers out there. Some really good early work was done here at Berkeley. Professor Meyer and Ranjit Garpuri, and I worked on this problem a bit myself during my master's. There's some really recently some really good work and simulation tools coming out of Oregon State University, Karti Myram and Terry Fiez's group, and different approaches to the problem. These are mostly mathematical approaches to dealing with this, how to solve the problem, and then how do you simulate a large circuit. And some of these techniques actually made their way into simulators like Cadence, but they're, I would say, rarely used because they're difficult to use and they really slow down your simulation. Okay, let's talk a little bit about the, I think we covered this already. Yeah, covered this. Yeah, another way to look at this, this coupling problem is to just plot isolation in dB. So this is a low resistivity substrate, so it's kind of like an epi substrate, and you can see that the characteristics are, just as we expected. As a function of distance, the coupling is roughly constant, and the isolation that you're getting is a very strong function of the ground inductance. So if you go from 5 nanohenries down to 1 nanohenry, then you're increasing your isolation from 40 dB up to 60 dB. And kind of a back of the envelope number that I carry in my head is, yeah, I can get 60 dB of isolation because I can put a good ground on my backside. And so usually package coupling will then dominate. Package coupling, if you're not differential, could be as bad as 30, 40 dB. If you go differential, you can probably bring that up to 50, 60 dB, in which case both effects are important. So if you have an amplifier with more than 60 dB of gain, right, potentially you're in trouble because the substrate and package isolation is less than that. Here's the numbers for a high resistivity substrate, and you can see that now the coupling is not that strongly dependent on the backside ground. Why is that? Well, the current's not going as deep, right? Okay. So here's kind of a summary of the guard ring. We've already talked about this. Marginal improvement in case of a heavily doped substrate or an epi substrate. Use a dedicated ground. Be careful about the package because ultimately the ground bounce and supply bounce in your package may dominate the coupling. Spacing does help with isolation, but not as much as you think. Some guidelines on designing guard rings. I'm going to kind of just stop there about substrate. Let me just ask you guys a question. Why do we use, actually I asked this question already, why do we use this highly conductive substrate? Well, it's to prevent latch-up, right? And latch-up occurs, whenever you're doing layout, be very careful if you've got an NMOS device close to a PMOS device, because an NMOS device and a PMOS device that are close together form a latch and can very easily ground your supply to ground through a very low resistance node. And it's actually kind of so usually latch-up is explained with this equivalent circuit. Say, okay, I have this positive feedback, this is an SCR. If I have enough current gain in my devices, then this thing will latch. Positive feedback will start, and this will just ground. This will short VDD to ground. Okay. There's perhaps an easier way to understand latch-up, and let me see if I can just explain that to you guys really quickly. So let's say I have my NMOS device and my PMOS device. So this is a P substrate. This is an N sub. It's connected to VDD, so I reverse bias this junction. And let me just start out with an electron. Let's say that somehow or another I've got an electron in my substrate. Well, if you're an electron in a p substrate, you're a minority carrier, right? So you don't have much chance of survival. But let's say you're a lucky electron and you just happen to come nearby this well, and then because you're a minority carrier, you're going to get swept across into this N substrate. So you're safe, right? Now in the N substrate, you're a majority carrier. Nobody's after you. You're in good shape. And so what happens? Well, what happens is that because you're an electron, in fact, there's a very good place for you to go, right? You can go to VDD. And in the process of basically this electron traveling and going into VDD, because this is a resistive material, there's going to be a voltage drop developed across this material, right? And in fact, because this is held constant by VDD, most of that voltage drop is going to occur in the well. So the act of this electron traveling across here will charge the N substrate, or sorry, N tub, let's say, or well, a little bit negatively, right? Which tends to forward bias this junction just a little bit, right? Now remember, even though this junction is reverse biased, that doesn't mean no carriers cross, right? It's just a statistical thing. It's just very unlikely for carriers to cross. So the act of this electron crossing and lowering the potential just ever so slightly increases the chance of a hole also coming across and taking the opportunity, right? So a hole gets injected into this well, right? And now as a hole comes here, let's call that H plus, as this hole comes into this well, it could also recombine, or if it's lucky, it will get swept across and go into the substrate, right? Now when the hole is in the substrate, it's a majority carrier, so it can flow, and in fact, it might so happen to come across your little NMOS device, which is close by, and also, which is again a reverse bias junction, and it'll go flow to ground, right? Now what happens? Again, this is a resistive material, so the fact that the hole crossed here and went to ground charges this point a little bit positive, which just a little bit forward biases this PN junction, right? Which means another electron gets injected, right? And I think from here you can see what happens. I have positive feedback. A couple more electrons here, do the same thing. A couple more holes. Now a few more electrons. Now a few more holes. And it just keeps going back and forth. And eventually I've got a dead short from VDD to ground. So that's how latch-up happens. And that's why this distance is so important in preventing latch-up. And that's why the resistivity is also very important, because the more resistive the substrate, the more voltage drop we get with minority carriers flowing. Okay, so that's just a brief overview of latch-up. Again, there's lots of literature and lots of techniques on latch-up. In 5 minutes, I'm not going to teach you all that, but it's something that you should be aware of. Anytime you put down an NMOS and a PMOS transistor, think, uh-oh, latch-up. So, okay. So that covers the coupling lecture, the topic, let's say, not lecture. And we're going to start a new topic. Any questions? Okay. So our next topic is device matching. And for analog circuits, it's extremely important, because ultimately we know that many of the circuits that we build are matching limited. If we're building A to D converters, if we're building comparators, at the end of the day, somewhere matching comes into play, and it can really ultimately limit the performance that we can get. So there's actually different kinds of matching, and just the fact that from wafer to wafer you're going to get different properties, right? Things are going to get doped differently from wafer to wafer. They're going to get etched a little bit differently. There's long-range matching issues, like you have gradients on your chip, right? If you look at a photo of a chip and let's say the threshold voltage, you'll notice that There's actually a pattern to how the threshold voltage develops, circular patterns. So devices close to the center have a different value than devices on the edge. What we're really concerned about, though, is short-range effects, because we're not going to build a diff pair by putting one transistor here and another transistor a millimeter away. We're not that stupid, right? We're going to put them right next to each other. So what we're concerned about is if let's say, if this is my diff pair with one transistor and another transistor, how well are these transistors matched? And it turns out that I'm concerned about properties of this transistor in this area. So for instance, what's the net doping in this area? What's the net doping in this area? How does the net doping vary from here to here? Because that's going to determine, let's say, my threshold voltage. So in the model that we're going to discuss, the mismatch model, again, it's going to be short-range effects due to random processes, not due to systematic problems. And so things like dopant fluctuations, mobility fluctuation, oxide trap variations, these are things that are going to come into play and change the properties of our transistor. We're not going to try to deal with these other systematic long-range variations. Now, the de facto reference for mismatch is actually a paper by Marcel Pelgrom. And Marcel Pelgrom, the very old paper in 1989, came up with his model for mismatch. Title of the paper is Matching Properties of the MOS Transistor. I encourage you guys to read that paper. We're going to have several slides here from that paper, but we're going to skip the mathematical derivations of the paper. And the mathematical derivation is actually interesting. A more recent paper, 2002, talks about mismatch data and a mismatch model for a 0.18 process. So something that you guys are all very familiar with, something dear to your hearts, 0.18 CMOS. You can now find out how the mismatch properties vary for 0.18 CMOS. Okay, so one of the assumptions in the mismatch model is that you have a Gaussian statistics, the normal statistics. And the idea is that you've got lots of single events, they're identically distributed, but they're independent, so at the end of the day, you end up with the sum of a large number of independent variables and you get normal distribution, right? Central limit theorem. And we've already looked at mismatch, but we only looked at it in terms of, let's say, for instance, we analyzed the current mirror and we said, well, how much is the current different between these devices, given that there's a threshold mismatch, given that there's a beta mismatch between the transistors, and so on and so forth. But we had no idea how to control the mismatch, right? The beta mismatch was a given, the threshold mismatch was a given. What we like to know is, how does those things vary with the layout of the device? And Pelgrom's model is exactly that. Pelgrom's model actually has a mathematical proof that if you're interested in a given parameter, right, this might be your threshold voltage, the standard deviation of that parameter is actually proportional to 1 over the area of the device. Okay, and it's very simple, but it's essentially the most important feature of the model, that as you make your devices larger, the standard deviation goes down. The part that you don't control is this coefficient. So this AP is some process-dependent coefficient which tells you the scaling factor. And so if you're given a new technology and you have to characterize it, you can go measure the VT of 100 different devices with different W's and L's, and then you try to fit the variation of VT to this equation. And you'll find that, in fact, if you take square root of this to get a voltage, that the variation will fit 1 over square root of area very well, and the slope of that line will be this sometimes called Pelgrom coefficient. Okay. Now the second term here tells you that just as you would expect, the standard deviation goes up with distance. Put things far away, they're going to be more mismatched. And for the most part, we don't care about this term as much. Can we zoom in on this equation? I didn't realize it was so small. The second term here, dx, is the distance between the devices. usually the distance is small enough that this effect is not so important. So this is really what dominates for the most part. So it's that simple. If you want to improve the mismatch, make your devices bigger. Yes.
And how well does this equation hold for short channel devices? Here it seems like as long as W times L is constant,
It holds pretty well. And in fact, the paper, the reference with 0.18 was one of the first verifications that it works pretty well. If you look at the derivation of this equation, it has nothing to do with short channel devices or long channel devices. It's a statistical argument.
But it seems to me it probably around for same area, it seems like a short channel, bigger W would have worse matching than longer L and smaller W for same area.
So at the end of the day, you're looking at, what's the net charge that you could get, let's say, in a region. And I guess what you're arguing is kind of like if your device has a very bad aspect ratio, then in this dimension, you might in fact be dealing with individual dopants, right? You're absolutely right. In that case, the variation goes way up. So this assumption here is that average quantities make sense. If you're talking about a transistor that's so small that a single dopant will make a difference to the threshold voltage, then yeah, this model doesn't work. But usually in analog circuits, we're not dealing with that. In digital circuits, you do lay out minimum size devices. In analog circuits, usually they're big enough, so this is not a concern. This is some data basically showing you that you get a reasonable fit to this equation.
Excuse me, I just
Yes.
questioned the previous
Yeah.
question. Well, I know that analog use like large W over L, but typically when we do the layout, it's like a finger cross stuff,
Yeah.
right? So it looks like the single transistor, the L is still the minimum size. How, right?
It's not really, I mean, so you have basically, your argument is that I'm going to lay out my device like this, right? And this is device A, this is device B, right? So usually, and we're going to talk about this more towards the end of lecture, if I have a fingered device, I can actually improve the matching, because what I can do is I can now intermingle my devices. So multi-fingered devices have better matching because of this intermingling. So now, if these two devices, right, have a certain mismatch because there's some kind of, let's say, some kind of effect that's causing devices in this direction to have, say, a higher VT, then now this device also has a higher VT. So on average, these VTs balance. So multi-finger tends to help rather than hurt you. Yeah.
And in fact, it doesn't decrease the L, right? If you split the fingers, you just scale W. The
Yeah.
L stays the same for each finger.
Yeah, this is the same W, and the L, of course, is constant. Yeah. Okay, so here's some data. This is raw data from the paper, Pelgrom's paper, and it's showing you that in this technology, it's quite an old technology, so it's, this is your grandfather's technology, 2.5 micron. But in this technology, you're looking at, standard deviations on the order of 10 millivolts for small devices. And then if you make your devices large enough, you can get this down to millivolts, right? Which is where you'd like to be in most applications. It's lots of data here. I'll let you look at this. This here is just showing you that, let's say, the threshold mismatch is not a function of VDS. So as a function of VDS, it's almost constant. And that makes sense. On the other hand, if you look at the threshold mismatch, it's a strong function of VBS, right? Why is that? And remember, we're not looking at VT. We're looking at the variation of VT. So why would the variation of VT be a function of body bias? Well, it's a little more subtle. The reason is that you have non-uniform doping in your channel, right? Usually the surface of the channel is doped higher than, if you go a few microns down or a few tenths of a microns down. So as your depletion region width gets larger, then you're uncovering a different set of dopants, right? And originally it's just the VT implant, but then you're uncovering the body dopants. And the statistics of the VT implant dopants are different than the body dopants. And so that's why you see a dependence on VBS. Okay, so it's a little bit subtle, but it does make sense. Okay, if you, at the end of the day, again from this paper, if you look at the, no, this is from the 0.18 micron paper. If you look at the mismatch you can get in current mirror, obviously it's very dependent on VGS, right? I know it's weakly dependent on VDS, but it's very strongly dependent on VGS, and we know that, right? We analyzed the mismatch in a current mirror, and we know that it scales like 1 over VGS. The other interesting thing is that if I bias it at a very high value of VGS, so if I'm looking at a mismatch in currents, there's roughly two effects, right? There's a VT mismatch and there's a beta mismatch. So if I'm in this regime where VGS is very large, which one dominates? Yeah, the beta mismatch, right? Because VGS is large, so if VT varies a little bit, it doesn't matter, right? VT varies 10 millivolts, well, VGS is 2 volts, who cares? So at that point, beta mismatch really dominates the current. If I go to low values of VGS, then VT mismatch dominates the current.
Which one is usually better controlled by the process?
It's a good question. Don't have a good answer for you. I think that it's really strongly process dependent. Yeah, but usually if you're designing a current mirror, you're going to have a large value of VGS to minimize the VT. So probably VT is the worse off. Okay. This is some data again from Pelgrim's paper, and it's showing you beta mismatch. So this is a standard deviation of beta normalized to beta as a function of device. And so you can see here, in answer to your question, in fact, we can compare that to the threshold mismatch. The VT mismatch is on the order of 10 millivolts down to millivolts. So in this process, you probably had a threshold voltage around a volt or so. So still, it's hard to tell because this one's normalized. But here you can see that relative beta mismatch is anywhere from 1% down to negligible if you make the device large enough. Okay. Now there's some other effects that are important, but they're simple to solve. So if you try to come up with a mismatch model that took into account orientation of the device, it would be a PhD thesis, but it would be very useless. Nobody would care, because just don't put them in different orientations. Just put them in the same orientation, and the matching is better. And you see it here. So you have almost several order of magnitude improvement when you use the same orientation. So if you're worried about matching two devices, put them close together, put them in the same orientation. This here is showing you the effect of variation of threshold voltage and beta as a function of distance with two different devices. And you can see that there is a small increase in variation, but it's actually not too bad, not as bad as you might think. So this is some of the interesting data from the... So this is kind of the summary. At the end of the day, the nice thing is you have hundreds of measurements, but they're really just captured in these coefficients. So this is the VT, this is the coefficient for the VT mismatch, for the NMOS and the PMOS. And the units are millivolts per micron, because remember, we're taking square root. So it's square root of area. That's why we get the micron here. This is our beta mismatch. This is a percentage times micron, again, divided by area. And then this is the The K factor here is also what's the gamma factor. It's the body effect coefficient mismatch. That's very small. Usually people don't even look at this. Let me... So again, these are just some curves showing you if you're designing a current mirror, obviously you're going to bias it with high VGS. And this is a measurement versus model mismatch. And you can see that this simple model with these coefficients that we looked at very accurately tell you that as as a function of VGS and as a function of geometry, for this current mirror, you're going to get 0.2% matching. Well, scaling has always been bad for analog, but in certain ways, for a couple of things, it's better. For FT, we all know it's better, right? You get faster transistors. It turns out that it's also better for matching. So as we scale technology, if you look at the coefficient AVTO, it's actually going down. And so that means that modern devices like a 0.18 device, this is from that second paper, if you look at the coefficients, they're actually better. They're smaller than a 2.5 micron device, substantially smaller. And so this is a good thing. That means that we can take advantage of this. In fact, it goes hand in hand with speed, because now we can lay out a larger device and not have as much speed penalty because our FT is so much better, and obtain good matching as well. So this is a pretty detailed device, and you can see that really what you should care about is this column. This is, if you want a slightly better match, then you would have an area-dependent match, and then a length-dependent match, and then a width-dependent match. But really, it's, again, this is what dominates, this first column. So this is your, again, VT mismatch, your beta mismatch. These are some coefficients that take into account some short channel effects, so velocity saturation mismatch. There's also a Dibble effect. This is a series resistance mismatch for our device. And in this particular paper, they lump the Dibble effect and some other effects into this velocity saturation mismatch coefficient. These rows are are correlations between coefficients, and usually you're going to just neglect correlations, right? Make life easier. So there's NMOS data, PMOS data. Here's some of that data from that paper. Let's zoom into these graphs. You can just zoom in onto this graph first. So this is a VT mismatch as a function of 1 over square root of area, and you can see that increasing the area, we can get down to millivolt levels of mismatch. So in very high precision circuits, we would operate here. But even, a lot of circuits might be able to tolerate 10 millivolts mismatch. Maybe we have offset cancellation, so you don't have to necessarily use very large areas.
So with the scaling, you said that the variations get smaller. Is that relative or absolute? Like
it's
that normalized to the exact?
It's
VT?
normalized to, basically normalized to the. So for the beta, it's normalized already. For VT, it's actually absolute getting better for VT. But your VT is also getting smaller, so at the end of the day, the normal and the absolute are kind of tracking, right? Because the VT variation is getting smaller, but your VT is also getting smaller. Yeah. So, and the good question actually for you guys. Maybe one of you guys know process better than I do. One of the reasons it's getting better is COX. COX is getting smaller, and if you do the math, you find out that having a larger COX helps. But then also to design smaller and smaller transistors requires better and better control of your process. And so one of the reasons that these devices perhaps have better matching is that it's just a better controlled process. The equipment has gotten better, the techniques have gotten better. Maybe someone in this class spends a lot of time in the micro lab, and they can comment on that. Anybody? Drew, do you have any comments about matching?
Well, I don't remember offhand the numbers that I've seen for absolute VT mismatch, but I think these days we don't consider T-ox variation to be much of a concern, and I think that just more generally speaking, we consider VT variation to be more of a problem, though I'm not sure if the absolute numbers are
And that's
bigger.
mostly due to dopant fluctuations.
That's right.
Yeah, yeah. Yeah, I mean, with these short channel devices, one issue which was brought up already is the absolute number of dopants you need is very small. So you're getting into the regime where just 10 dopants more gives you 5 millivolt offset. And so the absolute number of dopants is not very well controlled. And so that is definitely an issue for extremely short channel devices. But up into 0.18, 0.13, that's not too much of an issue. It's really, I would say, even 90 nanometer is not a huge issue. 65, 45 dopant fluctuations starts to be a big problem. Okay, I won't crunch through the numbers here, but you guys have done the math already in the homework. This is an equation for current mismatch for a current mirror, and given a certain value of VGS effective, right, GM over ID, you can control the mismatch. So for this particular example, to calculate the standard deviation of the VT mismatch, we plug in the area of our transistor. We use this coefficient here, and we find the standard deviation is 1 volt for this large device. In fact, a lot of times when you design devices, you intentionally make the device much larger than it needs to be just to get the matching. Also, if you calculate the beta mismatch, again using the coefficients, because beta is also function of W over L, you have to be a little bit careful when you apply the beta mismatch. So there is this component that goes like, right, beta is proportional to W over L. So you have to multiply the standard deviation by W over L squared. And this is where this equation comes from. And so at the end of the day, you plug in for 200 millivolt V star, you get less than 1% standard deviation for this current mirror. Okay. And then a second example is a diff pair. And what's interesting about the diff pair is that for current mirror, we're trying to match currents. And that dictates using a large value of V star, right? For a diff pair, we're trying to match voltages, and so it has the exact opposite effect. What we want is a low value of V star, right? The low value of V star minimizes the mismatch in beta, right? For V offset, threshold mismatch is already there. We can't do anything about that. And so there's no bias dependencies here. So as a function of bias, I can try to minimize the second term. And again, plugging in some numbers, you find that for the diff pair, you're looking at about 1 millivolt offset voltage for the same geometry transistor. Okay, so really the takeaway point is that next time you have to do a real project in analog design, look in the design manual, and if you don't find it, ask somebody, what are the matching coefficients for the process? Because this is a really important part of your design. Doing good layout is also helpful, and we'll go through some layout techniques relatively quickly. We talked about some of this in the beginning of the class, and I think I'll just highlight those things again just to remind you. So when we're doing layout, there's a lot of tricks, let's say, that you can use, clever things that minimize matching, basically, minimize systematic errors especially. So there's two kinds of techniques. We want to minimize proximity effects, orientation effects, right? And that means that we want our transistors to kind of be surrounded by the same kinds of devices so that they match really well. So I can very easily introduce a mismatch if I put one device close to a big well and the other device not close to a well, right? Because the etching will be a little bit different close to the well, and there'll be a stress from the well, and all sorts of things will change one transistor relative to the other. So I don't want to do that. Those are the things I can do to help here. I can also try to combat things like gradients, right? Process variations, temperature gradients, stress gradients, by using things like common centroid. And using these two techniques together, I can work really hard to get my mismatch down to an acceptable level. So as you can see now, when you're actually doing layout, there's some conflicting requirements. When you're doing your design, you want to make everything small and fast, and then when you think about mismatch, you realize that actually I want to make things big. And so you might not use the shortest channel length devices, right? You'll use the largest ones to get the best matching, largest ones that meet the speed requirements. And also, because you're using larger transistors, you have more capacitance. It means more GM, means more power, naturally. And there's kind of three regions that you can typically operate your circuits. If you need, let's say, moderate 3 sigma matching of about 10 millivolts offset voltage and current matching on the order of 2%, you don't have to be a great layout person to make this happen. Just doing some simple things will get you there. Don't misorient devices. Orient them in the same way. Use unit element style, right? In the beginning of class, we talked about if you have a W over L of 100, and you're trying, and you're trying to match it to another W over 100, it's better to actually use unit elements and intermingle them. And we'll talk about that a little bit later more. That'll get you down to this level, 3 sigma, 10 millivolts, 2%. If you need better than that, then almost all the techniques that we're going to talk about have to be applied very, very judiciously to get down to 3 sigma of 2 millivolts and current matching of 0.1%. If you need more than this, you're going to have to pay. You're going to have to do calibration, either post-process or on-chip calibration, or use some kind of tricks and techniques. And so unit element, there's not much to say here, right? Just use the same equal W, and instead of changing W, change M, right? So if I'm doing a matching of 2 to 1, let's say it's 5 to 1. This might be the bad way to do it, right? The good way to do it is like this, and maybe better way to do it is you tile it like this, and in fact just use even numbers. Avoid using odd numbers. Even numbers let you do things like common centroid. Okay, another obvious thing, make your devices large, right? Not much to say. Another obvious thing is think about the bias point. If you're doing current matching, right, you want large V star. If you're doing voltage matching, like diff pair, you want small V star. Okay, not much to say there. Same orientation, again, we talked about that. Compact layout. So obviously you want to make things as small as possible. Keep things as close as you can. Just keeping them close together will help. And then also you want to avoid awkward transistors, right? You would never lay out a W over L of 1000 over 0.35 as just one thin sliver. I mean, even if you didn't care about speed, right? The gate resistance is going to kill you. For matching purposes, if you lay it out as one thin sliver, then the left-hand side of the transistor is different from the right-hand side of the transistor. Has a different VT, has a different beta value, right? And so your entire transistor, if you're now trying to match that to another one, which is smaller, right? It's basically a gamble. Who knows which way it's going to go? But if you break it up into fingers and you make it more compact, then not only is the AC performance much better, but the matching properties are much better. So common centroid, we talked about this early in the class, first or second lecture. When we do common centroid, what we'd like to do is So the word common centroid really means that the effective geometric center of each device should fall on the same point. So if I had, let's say, two devices like this. This is device A, this is device B. Kind of the center of this device is somewhere here. The center of this device is here. So their centers are different, right? And on the other hand, if I put my devices like this, now the center for this device is right here, for the A device, and the center for the B device is right here. So they're, if you like, the center determines the average properties, and so because their centers are coincident, on average they're going to look the same. Of course, we're going to make sure they're oriented in the same direction. We're going to make them as compact as we can. And by doing this, what's going to happen is that any kind of gradients that we have, so there could be like a large-scale process gradient. So let's say these are curves of constant Vt. So this is plus 1 millivolt, this is plus a half a millivolt, maybe this is minus a half a millivolt, and this is minus 1 millivolt. So these two devices are actually, this one has 1 millivolt, 2 millivolts higher Vt than this device, right? But the average Vt for this device is about 0 millivolts away, right? Because half of it's 1 millivolt higher, the other half is 1 millivolt lower. This device, on the other hand, falls on a constant Vt contour. And so it's, in this case, it's going to have half a millivolt less Vt. Well, I really exaggerated here this gradient. If this is a tiny device, these are actually going to be straight lines. And for straight lines, this common centroid would actually cancel out any kind of Vt mismatches. The other thing that we do is we use dummy segments. So dummy segments, the idea is if I have a multi-finger device, let's say this is my first device, and this is my second device. And I need them to match, right? They're different sizes, but they should match really well. What's the problem with doing this?
The dummies, well, the fingers on the left and the right are going to be thinner because more etchant is consumed in the middle than on the sides, and therefore the etch rate for the ones on the sides will be much faster. And in this case, the 6 on the left and the 3 on the right will not match.
Okay, very good. Yeah, exactly. So the rate at which you etch, right, if to get into the middle of these two fingers, right, is going to be a slower process than to get to the edge, right? The etchant can come all the way, and so these devices will end up being thicker after etching than the side devices. And so what happens is here I have 3 fingers, 2 thin, 1 thick. Here I have 4 thick, 2 thin, right? And so basically I could have done something to completely avoid this problem altogether. I just add dummy fingers. So I add fingers here which are not being used. They're just there to make my device more symmetric. And so now these 6 and these 3 fingers see the same environment. So each guy looking to the left and right sees the same thing. The person at the end to the left doesn't see a finger, to the right sees a finger. So this will get messed up. But who cares? We're not using that guy. So always use dummy fingers. Something else that a little bit more subtle is stress. And the idea is that because different parts of the chip feel different mechanical forces, or because different materials have different thermal coefficients, you end up getting local stress. And that stress will change the properties of your device. It'll change your threshold voltage, for instance. So if you're, how do you solve that problem? Well, first of all, either make sure that your devices see the same stress, or better yet, don't see that stress, or that's the solution to the problem. And so things like you wouldn't expect, stress from the package, just the fact that the edges of your device have bond wires going to them or solder bumps going to them, they have different stress than the center of the device. So the center is probably the best place if you want to avoid stress. If you can't avoid it, this is what I was going to say earlier, is you use common centroid layout, because the stress, again, is some kind of gradient across your chip, and by proper layout you can minimize its impact. Metallization, again, because metals are different materials than the oxide and the silicon, they have different thermal expansion rates, and so they will introduce stress locally on a device. So if you have different metallization around one device than on another device, let's say you have two devices, and this device is close to a wire, let's say a couple wires coming across, and this device doesn't have these wires going over it, this device will have a different threshold voltage than this device. And this is something you could have avoided. So either move these transistors away, or maybe just put dummy metals here to make them the same. Okay?
Yeah, could you explain in details how does this mechanical thing affect those electrical?
I can't explain it. No, there's all sorts of crazy things going on. Mechanically, what happens is the band gap changes of the material. So it's a lot like putting stress on a device and changing its mobility, right? Lots of detailed physics. Who knows what's going on? Contacts. Again, same thing with metals. Make sure that the way you contact the device is the same. Really avoid putting metal on top of your device if you can. This stuff is all obvious if you think about it, but you just have to sit down and think about it. Make things the same as much as possible, right? One thing that, coming back to this idea of stress, is even though you can put things very close together in a modern CMOS process, you might not want to do that. And that's because junctions, so like let's say this is one device and I have two devices here that I want to match. This distance, let's say this is a well, will impact these devices, and the devices that are closer to this well will feel more stress than devices far away. This is called STI, and it's basically the oxide, the trench isolation, that's causing stress on these devices. So what does the STI stand for? Is it shallow trench isolation. So it's the shallow trench that surrounds this device that actually creates stress. So devices that are first of all close to the edge, right? There's a design rule that says you can be so many microns away from the edge. Well, don't take that minimum, because the device on that edge is going to get stressed. Okay. Also, look at your data carefully. Your NMOS device may have different parameters than your PMOS device. One may match better than the other. So, for instance, from that paper, the 0.18 device, you see the VT of the PMOS has better matching, about 2x better. Why? I don't know. NMOS device, though, the beta is much better. So if you're trying to do voltage matching versus current matching, right, you would choose different devices. One final point is temperature, something we usually don't think about. But if you look at the temperature dependence of threshold voltage, it's about 2 millivolts per degree C. That's huge, right? If you've got a transistor that's driving an external load and it's dissipating tens of milliwatts, maybe hundreds of milliwatts, it's going to run hot, right? And so that's going to create a temperature profile across your die. Where the power transistor is, maybe you're 10 degrees hotter, and then as you move away from that power transistor, the temperature drops. So if you're designing, again, matched transistors, make sure that first of all you use techniques like common centroid, but sometimes using common centroid is cumbersome. The parasitics of putting everything in a common centroid outweighs the benefits. Well, if you know that your device is here in your layout, so this is the power transistor, right? You can probably guess that the thermal coefficient is going to look something like that. Sorry, really bad drawing. So as long as your matched device is oriented like this as opposed to like this, it's probably going to be okay. So think about temperature effects in your chip. And think about where temperature is being removed from your chip, right? It's important. Okay, a couple more points about the common centroid. I think I've heard a lot about this already. Kind of the central idea of a common centroid is divide something big into lots of segments, right? If you have a big capacitor, use a bunch of unit elements to build it up. Okay? And this is kind of a repetition. We talked about it already. One thing we didn't talk about was this concept of dispersion. So lay out your device in such a way that it has what's called here high dispersion. And the idea being, I like to think of it more as intermingling. Take your device and make sure they're as intermingled as possible. So the worst thing you could do is, of course, usually you're going to lay out your device. These are fingers, right? The worst case would be this is all fingers for A, this is all fingers for B. That's the worst matching. Much better is to go something like, this is the best case. Put device A, device B, device A, device B. So, abab, baba. If you forget the best way to do it. So here's a little bit more detail. So this is the drain, the source, the drain, right, in a multi-finger layout device. So this is our standard common centroid layout. As we divide it up into more and more unit elements, we can do something like this and maximize the amount of intermingling we have. And at the end of the day, what we're doing is we're fighting linear gradients. So any kind, you can sit down with this thing and play with it and show that no matter which direction the gradient flows in, this thing will combat it as long as it's a linear gradient. Okay, I think this is a good place to stop. Next lecture, we're going to talk about MOS sample and hold. And so we have 2 lectures next week. And then the last lecture will be a guest lecture because I'll be out of town. So if you have questions and concerns about the project or about homework, please come to office hours today or Tuesday. Because again, Thursday I'm going to give lecture, but then I have to go out of town. So today and Tuesday are the best days for office hours. If you can't make those days, send me an email and we'll make an appointment.